Hello and hi everyone. So we are from group Quantum Synchrony that will present about superfluidity, which is the quantum dance of liquid. So these are our group members. From left we have Amirul Azwar Binti Aziz. Next one we have Aisha Dalila Binti Aziz. Next we have Aina Mazliyana, and lastly we have Fatin Dalila Binti Mahadhir. So without wasting our time, let us talk about superfluidity now. So now we are going to talk about the superfluidity, which is the quantum dance of liquid. So what is it? Superfluidity is a special state of matter where a liquid flows without any resistance. This means it moves without losing energy or slowing down, even through tiny spaces or around obstacles. It occurs at extremely cold temperature, which is close to absolute zero, when particles like atoms behave in a unique collective way, almost like a single quantum wave. This is the quantum dance of particles. Next, I will explain more about superfluidity. Superfluidity is a fascinating quantum phenomenon observed in a certain fluids that at extremely low temperatures exhibit unique and counterintuitive behaviors. The most common example of superfluidity occurs in a liquid helium, especially in helium-4 and helium-3, which when cooled to below a critical temperature lose all their viscosity and can flow without any resistance. This means that a superfluid can move through narrow channel or rise up the walls of its container, defying the normal laws of fluid dynamics. Next, we're gonna explore about the theories behind superfluidity. The explanation for superfluidity comes from quantum mechanics and the concept of Bose-Einstein, which is BECS. At a very low temperatures, particles in a superfluid behave as a boson particle that obey Bose-Einstein statistic, and they can occupy the same quantum state. This creates a macroscopic wave function that allows the fluid to flow without any friction. For helium-4, the superfluidity is due to boson-like behavior of a helium atoms. For helium-3, which is a fermion, which is the particle like electrons, superfluidity arises from the formation of Cooper pairs, which is the pairs of fermions that act like bosons, similar to the mechanism seen in a superconductivity.
Quantum theory of superfluidity. The key quantum concepts involved wave function overlap, which the wave functions of particles become coherent across the entire system, and macroscopic quantum state. A collective behavior emerges governed by the same wave function. Bose-Einstein condensation (BEC) applies to bosonic particles like helium-4, at which at low temperatures a large fraction of helium-4 atoms condense into the same quantum ground state, forming a Bose-Einstein condensate, which has zero viscosity and collective quantum behavior. Fermionic superfluidity. This applies for fermionic particles like helium-3, which cannot form a Bose-Einstein condensate directly due to the Pauli exclusion principle. Fermionic atoms pair up due to weak attractive interaction, and these pairs behave as composite bosons and undergo Bose-Einstein condensation. Quantum properties of superfluidity are zero viscosity, quantized vortices, phase coherence, and critical velocity. Landau's two-fluid model. Normal fluid component consists of thermally excited quasi-particles, phonons and protons, and superfluid component, which is a zero entropy and quantum coherent phase. Quantum excitations play a critical role. For phonons, low energy excitations correspond to sound waves in the fluid, and for protons, high energy excitations associate with local rotational modes. Theoretical models. Gross-Pitaevsky's equation describes the dynamics of the superfluid's wave function and is useful for Bose-Einstein condensates. Experimental evidence. Fountain effect, flow against gravity due to quantum pressure, quantized vortices, which are seen in rotating superfluid systems, and persistent currents, which are continuous flow in ring-shaped containers. Superfluidity is also closely related to superconductivity, where the electron pairs form a quantum coherent state. Both phenomena are governed by microscopic quantum wave functions and exhibit similar excitations.
Moving on, these are the properties of superfluidity. First, they exhibit perfect fluidity, which means no internal friction disrupts their flow, even at microscopic levels. Second, it occurs below a critical temperature where certain liquids, as example, helium-4 or helium-3, transition into the superfluid phase. Next, these are the hypotheses of superfluidity that's been listed by us. First, it serves as a platform to study quantum phase transitions and exotic states of matter. Second, it contributes to the advancement in quantum technology, including quantum computers and sensors. And third, it offers analogies for studying cosmic phenomena such as black hole event horizons and early universe conditions.
Next, let's move on to the characteristic of superfluids. The first one is zero viscosity. Superfluids can flow without friction, meaning that they can move through tiny channels without losing energy. The second one is quantized vortices. In a rotating superfluid, the circulation is quantized, leading to the formation of vortices. The third one is second sound. Superfluids can support a wave-like propagation of temperature variation, known as second sound. Here is the examples of superfluid. First, helium-4. The most well-known superfluid which becomes superfluid below approximately 2.17 Kelvin. It exhibits unique properties like the ability to climb walls and flow through the tiny opening. Next is helium-3. This isotope of helium becomes superfluid at even lower temperature, below about 0.3 millikelvin, and it has two distinct superfluid phases, A and B, with different properties. Other than that is ultra-cold atomic gases. Certain gases like rubidium-87 can be cooled to form a Bose-Einstein condensate, which can exhibit superfluid behavior. Now let's move on to the last part, which is application of superfluidity. First, cryogenic. Magnet resonance imaging semiconducting process as well as large and small-scale basic field work requiring helium temperature. It is the primary cryogenic application. The second one is magnetic resonance imaging (MRI). The superconductive magnets which are supplied with liquid helium as a refrigerant. The affordability of helium and the stabilization of the market has led to the fast development of MRI as a diagnostic tool. The third one is semiconducting process. The main helium users of the semiconductor industry are silicon wafer vendors. 12-inch, which is 300mm crystal, is used to stabilize the host poles of semiconductor material with a helium-cooled superconducting magnet. That's all from our group. Thank you.